And Paula, can you introduce our next guest, please?
Yes, the professor already is connected. I cannot see him account.
Yes, you are ready. Go ahead.
Okay. So hello everyone, welcome to the last talk of the FuseNet Master event. I am Paula and I will be hosting this talk. Then I have the pleasure to introduce our speaker, the Professor Ambrogio Fasoli. I will just highlight a few things about his bio, but if you want to know more about all these contributions to the fusion field, you can just type his name in Google and get all the information. He's a currently professor at EPFL in Switzerland, which he joined for the first time to do his PhD in physics. He went on to do his postdoctoral research on JET in Cologne, participating in 1997 in the experiments for fusion power generation, which has been the world record for 24 years until 2021. He joined the physics departments of the MIT as a tenure-track assistant professor, where he led the plasma physics research group and coordinated the international scientific collaboration between MIT and JET. Furthermore, he has been active in the world of fusion at many organizations like Eurofusion, the International Atomic Energy Agency, and of course the EPFL, where he's currently Associate Vice President for Research. So without further delay, I give the floor to Professor Ambrogio.
Thank you very much, Paula. I was trying to connect, so I missed the very first part of the presentation, but I guess I know my own thing. So I am very happy to be with you virtually this evening. And my idea, let me just try to share the screen, is to give a presentation. Let's see. Hopefully you see it now. Can you see the full screen?
Yes.
Or is the presentation mode? The presenter mode.
Presenter mode, Ambrogio.
So I swap this. So now it should be fine.
Yes.
Okay, great. So I give a somewhat strange structure of the talk, if you allow, because I will essentially describe a little bit our European approach to fusion, what we do in a consortium that is all of us together. But I will take the opportunity at some point to just go a little bit into one piece of physics that is close to my heart, and I will not go into many details there either, but I will just illustrate some of the things that we're doing in that aspect of burning plasma physics. So I don't pretend that it will be completely a physics presentation, but I hope it's not going to be a political presentation either, but more strategic in general, and that may be of interest for all of you. So of course you can interrupt me any time, though you have to speak up because in presenting, I don't see actually your faces or your hands up. So let me just start. So I don't know why it's not. Okay. So here is my layout. And as I said before, I will introduce a little bit to you what the Consortium Eurofusion is, what's the roadmap idea, which is our kind of a reference, if you like, approach to get to the reactor, although we are modifying that approach as we speak, because I just finished the meeting with all the people in the Bureau of Eurofusion to take that approach and modify a little bit, and I'll say a few words about that. So I will dwell on the 8 missions for a very short while, so to see how we articulate our program. And also I would like to speak to you about the adaptation of the program that we are undertaking from one cycle to the next, and what is our vision, and also what the objectives are for this cycle in which we have just embarked in terms of ITER, in terms of the stellarators, materials. One key point is in conceptual design for demo, and also a couple of elements on innovation in industry and education and training. And as I said, I will do very quickly and early in the talk, an interlude on elements of burning plasma physics. And then finally, I will introduce a keyword for all that we do, that is integration. So let me just clarify one thing for you, which I know it's sort of a boring policy kind of element, but I think it's important to understand one thing, that we have essentially three major stakeholders for fusion in Europe. The European Commission, which is sort of an overall sponsor, if you like, which has two directorates, like two ministries that deal with fusion. One is on energy, that is where ITER and fusion for energy are managed, if you like, from the European point of view. And the other one is research and innovation. That's where our consortium is. So you can see that it's really a little bit more on the research side of things. Then, of course, you have Fusion for Energy, which is the domestic agency. So that is the European agency that's responsible for the EU part of ITER construction, and also for the collaboration with Japan that came around because of the negotiations of where ITER should be built. And as I said, our consortium, which is Eurofusion, which conducts essentially all fusion R&D in Europe and supports education and training also via FuseNet. Now, about Eurofusion, it was founded in 2013, and this is the status as of today, with 29 countries. Not all of them have the same color. You can see that Switzerland, where I am, UK, where Jet is, and Norway, they are associated members. So Switzerland and UK participate by being, if you like, associated to the Max Planck Society and Institute of Plasma Physics in Germany. And via that collaboration, we can be part of the consortium as if we were in Europe, except that we pay our own expenses. Norway does that via the Danish participants to the consortium. And then we have an associate member, which is Ukraine. We're very proud of helping them at the moment as much as we can. 31 research institutions, 150 universities or thereabout, and about 4,000, depending on how you count exactly, fusion researchers and support staff. We're talking about big stuff. And more importantly, 800 students at master level or PhD level across Europe. Now, we prioritize our research along what we call the fusion roadmaps, a kind of a reference document. Now, this has been written over the years, and it's a dynamical thing that has to be adapted depending on the circumstance a little bit, depending on the findings also from the scientific and technological point of view. At the moment, this is the vision. We don't put dates at the moment because putting dates is always a little bit difficult. So we have a kind of short-term, medium-term, and long-term periods that we anticipate. And you can see that we have ITER and demo as two main elements, and they are fed with research on the present and planned facilities, on theory, of course, and on modeling. But we also have to look at materials, to look at Stellarator as a possible fusion power plant. And one of the things that we have to keep in mind is that we have to make the concept sellable. So we have to have a lower cost for fusion electricity through concept improvements and innovation. I should say maybe at this point that we're discussing at the very moment how to face the new boundary conditions, which are bad and good at the same time. Of course, bad because of the Ukrainian war and of the more urgent climate problem. Good in a sense that this at least raises awareness about the urgency that we have to undertake to go towards a fusion reactor for having clean baseload electricity source. And also good because they also bring about a lot of private interest and private investors. And we as a consortium, we don't want to just be completely separate from that. We are really opening our doors and thinking about how to adapt our structure, our functioning to have a collaboration between private and public. I think that is really very important, and especially important for you because you don't have to make a choice between, say, the traditional way of approaching fusion with public support, which is very long, maybe, and not very innovative necessarily, or the new way, which is maybe making false promises, but at the same time appealing because innovative and maybe shorter term. No, I think this dichotomy, we will attempt at removing it and combining the best of the two approaches in the next way, in the next few years, and in a new way we will approach this roadmap. The missions and the logical sequence of things will not change because they have been identified through decades of research, but perhaps we can parallelize more things, perhaps we can open even more to innovation. So these are the 8 missions, and now we go a little bit more into science. So one thing is what we call plasma regimes of operation. We need to understand how we can actually steer the plasma into one of these regimes, as we call it. So plasma is a highly self-organized system, very highly nonlinear, and the way we can put in one state or the other depends on how we set up the operation. And you can have different ways of setting this up. And we need to understand which one is the best, or which ones are the best, maybe more than one, for the real reactor. And that includes the core of the plasma, includes the way we manage the interface between the edge and the wall and everything. Second specific mission is about this aspect of how we exhaust heat and particles from the plasma, and which is the best configuration to do that without obviously damaging the wall, and at the same time without affecting the performance of the core and maintaining the stability of the whole system. Third mission is about materials, which have to withstand, of course, the huge neutron flux from the core plasma and maintain structural capabilities to perform their duties in the different parts. I will come back to that. The fourth mission is the question of tritium self-sufficiency. As you know, a lot of criticism of fusion is issued from the difficulty in getting tritium. And we have to fight this battle of producing our own tritium. And the battle is won or lost on the basis of a very small difference in a small number, which is the tritium breeding ratio, how much tritium we can produce per nuclear reaction. And that is an essential element. And it's easy to write down the reaction for producing tritium, between a neutron and lithium-6, for example, but it's very difficult to put into practice in a reactor environment with the proper materials and the proper coolant and so on and so forth. So this is a mission in itself. And the other two, I can quote them in together. Implementation of intrinsic safety features, because this is one of the advantages of fusion. It has to stay so, and therefore have that implemented in integrated demo design, which is an essential element on the way to the reactor. Oops, sorry. And to do all of that in a competitive cost, you see examples here of components that are actually built using 3D or so-called additive manufacturing, and they can be complex yet less costly than the ones we make today. And the last mission is the stellarator as an alternative to the tokamak. Now we work together. Together is a very important word for us. And this is a visualization of the joint operation of the different tokamaks across Europe to provide input for ITER and demo. Some of them already exist. Some are about to exist or about to be operated fully, like JT60. Some are a little bit down the road, like DTT in Italy, for testing the specific issue of the diverter concept. Now, what did we change when we went recently, or just now, in fact, from the previous program, framework program to the present one, so from Horizon 2020 to Horizon Europe? Well, we need to evolve to combine the preparations for ITER experiments with the demo conceptual design. Essentially, this is just the main element. But if you look at the division, repartition of the investments that we had, the budget that we had in a previous period, you have ITER physics, which is dominant, so-called power plant physics and technology, which was looking at more demo. a little bit more fundamental aspects called enabling research, and then training and education. And this is the, if you like, the division of tasks or programmatic lines that we had until last year. And now we're going to some more different things. So fusion sciences is including ITER and power plant physics, but also enabling research. And it's quite big, but it's not much bigger than ITER physics on its own. And what has really been expanded is the fusion technology, because we need to go swiftly towards the definition of demo. And also we have a very specific dedicated part of the budget and of the effort into the demo design. And one part that has to stay is, of course, training and education. So what are the objectives that we have for this coming, let's say, 5 or 7 year period, depending how you count? We need to contribute to the construction and the commissioning of ITER. We need to prepare ourselves for that. And when I say prepare ourselves for that, I need to prepare you, all of you, in a sense, all of our community. And we need to do that as one team. You know, it's a complex environment, and I have already probably bored you with the complexity of the environment at the very beginning, of course, with the different stakeholders, but we need to prepare the operation. By that, I mean, we need to also see where we lack competencies, where we lack manpower. How do we develop these competencies? How do we engage this manpower? How do we, you know, form the operators of ITER, and how do we participate to the operation of ITER? Because the ITER central team is relatively small and will stay small. And the operation of ITER is the most complex things we ever done. And so we need to really be involved in that with the proper competencies and the proper schemes to participate from outside. Wherever you will be, we will want to be involved in the operation of ITER one way or the other. And so you will need to know how you can do that as one team altogether. Now, we also want to optimize the chances of success, and this meaning developing scenarios, is meaning looking at burning plasma physics, control, plasma wall interaction, heat exhaustion, etc. And that's where I open my parentheses on a little bit more physics-based concepts. So I'd like to speak to you a little bit about burning plasma physics and taking only one aspect of it after having introduced some generalities. So let's go into that, if you don't mind. So just some generalities. I know some of these concepts are trivial to you, perhaps, but perhaps you haven't seen them in this angle. And let me just, in any case, remind them to you. So you all know that the fusion power density can be calculated as 1/4 of n square. That's because we consider 50-50, of course, deuterium tritium. Then the reactivity in the form of the distribution function average sigma times V. Sigma is a fusion cross-section, of course, and the energy released in a single fusion reaction. So that is my fusion power density. 1/5 of that is the power density in the alpha population, and the 5th fraction comes simply from the mass ratio, essentially, between alpha and neutrons. Now, if I look at the thermal energy density of the plasma, if you like the pressure, excuse me, that's 3 times the density times the temperature, assuming a common temperature for different species. And if I look at the energy balance, the variation of the thermal energy density is equal to the power input from outside, which is the power density, the total power from outside divided by the volume, so that the power density that's injected, and the power density from the alpha, the so-called alpha heating. These, of course, have a positive sign, minus the losses, which I just consider here in terms of convection and conduction, so represented by a single confinement time, tau E. So fusion energy gain is fusion power divided by input power, so that's about 5 times alpha power divided by input power. And the alpha heating fraction is therefore very easily calculated. It's defined as P alpha divided by the total power that heats the plasma, which then is Q divided by Q plus 5, which means that up to now, you know, the best capital Q we have obtained was in the JET 1997 campaign, so the so-called DT1. It was about 66%, so let's call it 0.7. So up to now, we have done not better than 12% of the fraction of alpha heating. Q equals 1 is 17%. And that is to say there is really a sort of psychological value for the break-even value of Q equals 1. 17% doesn't mean anything. You know, it's similar to 12%, if you like. It's not a game changer. What's really a game changer is when you get to 50% of alpha fraction. So that means you start heating the plasma more from within the plasma by its own fusion product than what you do from outside. So Q equals 5 is a game changer because that's the definition of the burning plasma regime. Burning plasma regime is when you have more 50% or more of heating that comes from within the plasma. So that's why Q equals 10 is important because then you are well into the plasma, into the burning plasma regime. Of course, Q is equal to infinity corresponds to ignition, which is 100% from the alpha, but we don't aim at that anymore in a modern approach to not only to ITER, but also to demo and the actual reactor. We aim at something like 30, 40 for demo and for the reactor, which is enough. We have an engineering gain that's that can make the fusion reactor work as a power station. So we are in this regime when we are more than Q equals 5, and that is, of course, the goal of ITER to be well into that regime, and we promise to make Q over the 10 or more, and for a fusion power over the 500 megawatts or more for several hundreds of seconds. We also say we can maybe look at steady state Q equals 5, but longer duration. This may be much further down the road. So let's concentrate on the one that is really the goal, which is Q equals 10. Just to give you an idea, the Q equals 10 scenario, which this is a simulation in front of your eyes. So this is the total power there with the alpha power, the auxiliary power, and the Q represented the function of time. We're talking about hundreds of seconds. So this indicates, I think, is 400 seconds. Just to give you a rough idea, a total alpha energy in a single shot of ITER is about 50 gigajoule. And the total alpha energy produced by JET and TFTR, DT companies, in other words, produced by mankind so far in fusion research, is less than 10 gigajoule. So one pulse of ITER would be more than the whole history of fusion in terms of alpha energy. And that is something that maybe we don't realize if you don't make this simple calculation here, which means it will be a completely different self-organization of the plasma. And this picture is extremely complicated, and the purpose of it is actually to show that it is extremely complicated. And maybe not complicated is not the right word, but maybe what I should say is extremely coupled. Everything is coupled. Is a complete interplay of plasma dynamics from within the plasma and external systems that we need to somehow master and somehow steer in some direction that we prefer. And I use the word steer because it's very difficult to control all the elements. So from outside, we of course provide heating. We provide injection of momentum. We can provide current drive, injection of current. We can provide maybe some specific fields that are there to control the error fields in the tokamak and the instabilities. Of course, we provide the flux with the colloidal flux with the ohmic transformer. We provide the particles by fueling. We pump the particles by pumps. We control the shape by the different magnetic coils. And we can have all our systems to mitigate or control the vertical displacement and the disruptions and the runaways. But more importantly, in the context of our discussion today, is what happens inside. The alpha heating dominates, and the alpha heating is dictated by where the alpha particles are produced, therefore by the fusion reactivity profiles, which are in turn determined by the profiles of density and temperature. they are all which are also determining the profile of resistivity and of the booster current, so the profile of the current in the plasma itself, which influences the magnetic structure. The transport is, of course, a consequence of the profiles and of the B-field structure, but it also is a cause of the fluxes of particles and heat and momentum, and therefore influences in turn the profiles, and so on. The profiles also influence the instabilities at microscopic and macroscopic levels, and so on. So all of that is strictly coupled with each other, and all the coupling, in a sense, is actually guaranteed, that we like it or not, by the fact that alpha heating will be central. So this is the new dynamical system that we haven't seen so far. We only see for the first time in an actual burning plasma, that is in ether. All we can do today, and it's not nothing, of course, but it's all we can do, is to look at the separate building blocks of this complex environment. And one building block that I like to discuss briefly with you is what happens in the context of the self-heating of the plasma. So again, we inject from outside power, and we unfortunately, all the system we can use in ether, at the end of the day, they heat the electrons, because they all create fast ions that by collisions, they essentially preferentially heat the electrons, because they are very fast, or we directly heat the electron with electron cyclone heating, of course. But in any case, then the electrons have to be thermalized, and they contribute to the heating of the plasma, which then fuses, of course, and the alpha power is supposed to be retained within the plasma. And that 20% of the alpha power from the fusion reaction is crucial, absolutely crucial in maintaining the reactivity of the plasma. Now, it takes quite some time for the alphas to slow down to the temperatures of the electrons and of the ions. And again, the alphas themselves, just like, for example, the fast ions produced by neutron beams, they are so fast that basically transfer the power primarily to the electrons by collisions. And that takes a long time. So a lot can happen in that time. And these particles are the last ones we want to lose, because they are the ones that maintain reactivity. So this idea of the self-heating process has been tested, and it's a really difficult experiment to prove. This was done in a very careful way in '97 in the JTP campaign that time, and still now people actually question the exact percentages and the exact conclusion. I believe this is a valid conclusion, nevertheless, that we have seen the electron heating from the alpha. So the self-heating process of the plasma, the slowing down of the alphas on the electrons, actually works. You may say, okay, sure, this is a simple Coulomb theory, but honestly, it's the only experiment I'm aware of that demonstrates this. So it's always good to have a demonstration, an experiment, and still it's not completely uncontroversial one. And you can see the axis here, the core temperature for the electrons as a function of the alpha power, which is varied by varying the DT fraction. And you can see that the vertical axis is actually not starting at zero, because the difference is relatively small. Nevertheless, you can think that you can observe there's quite a good correlation between the alpha heating and the increase in the electron temperature. To my knowledge, this is the only case in this history of fusion where we have seen a clear effect of the alphas on electron heat. Now, where do the fast ions come from in all the experiments and present and future? So of course they come from alphas, from fusion reaction in the form of alphas, and they can come from ICRH heating, and that would be the tail of the distribution, or from the injection of high energy neutrons from NBI. So this table is from this ether physics basis publication we had some time ago, and of which we actually prepared in the update, is to underline the differences that exist between the present sources of fast ions and ether. You can see the tau s is a slowing down time, not very different. So there we are in business. The concentration of the power in the core is not that different either in some scheme compared to the alpha power in ether. The density of the fast ions in the core also, we have even exceeded that one that would be foreseen for ether. The beta of the fast ions also been exceeded, and so has, and that is true for, or at least of the same order for the average beta. The gradient of the fast ion beta or the fast ion pressure is a crucial element because its drive for the instabilities are driven by the fast particles. And we have achieved that values that are of the same order or even larger, slightly larger than those anticipated in ether. The ratio of the velocity of the fast ions and Alfvén speed is crucial in terms of the instabilities we are about to discuss briefly. It's also something we can achieve in some cases in the present devices. What is different from what we can achieve now and ether or burning plasmas more in general is the size of the orbits compared to the essentially compared to the size of the machine. So that's so-called rho star. It's much larger in the present device than it will be in ether. And the slowing down of the particles is similar in absolute terms, but if you normalize the confinement time, which is an important element, is actually very different. It's much larger compared to what we have in ether. The other thing is that if you simulate the alphas with beams or with alpha or with ion cyclotron heated particles, the distribution in velocity space is not the same as those that are produced by fusion reactions, as the alphas that are produced by fusion reactions, because in both cases they are anisotropic. So in the case of beams, you have more passing. In the case of isoreach, you have more trapped because you heat the perpendicular degree of freedom more. So that is also different. So we can mimic some of the elements, but not all of them in present devices. Present and in near future devices, in other words, those that don't burn yet. So to conclude this part, we need to confine the fast ions during the slowing down, during the whole slowing down if possible. So we need absolutely to tackle anything that can happen to them in that slowing down. And we need to make sure we don't have magnetic field imperfections, so we can correct them, because they are going to be quite a disaster for the confinement of the fast particles, because they influence the orbits by trapping locally and having the particles drift out. We can see if there's an effect of the turbulence on the fast ions. Here, the good news is that the microturbulence actually is averaged by the big orbits of the fast ions. And so the effect of the microturbulence on the fast ions in general, at least for the case of ether, is actually much smaller than the effect of the turbulence on thermal ions. So this is where one of the few examples in which nature helps us. And so turbulence transport for fast ions would be actually probably irrelevant in many cases of interest, at least for ether. What is not irrelevant at all is the effect of not of microturbulence, but on more macroscopic instabilities and waves, typically those that we call MHD, because they are the waves and instabilities that arise within the MHD model and the MHD approach. So I will mention now a little bit what we do about that in one particular experiment that I'm very keen on, because it's something that I have contributed to myself for some time. But just to give you an idea also how you can have a very basic idea and apply it to actually a concept and problem that affects burning plasma. So I will speak a little bit about the resonant interaction between the fast ions and Alfvén waves, and why is that a potential fast ion loss mechanism. So you remember, I hope, what Alfvén waves are. So they are issued by the fact that the P field and the plasma are frozen together in ideal MHD. So the field lines can be seen as guitar strings that you pinch with the motion of the plasma instead of pinching them with a plectrum, and they are oscillating, and a wave propagates along the guitar strings that the field lines are, due to the fact that the field lines, like guitar string, are subject to tension, and of course they carry some inertia because they are attached to the plasma. Now, point is that in a torus, they have different, the geometry becomes a little bit more complicated and so on, but forget about that for the moment. The point is that the Alfvén waves have essentially one phase velocity, which is the Alfvén speed, and that it depends on the field and on the density. And the typical value in the conditions that we have in mind for the reactor or for ITER or even for present machines varies very little from machine to machine, because if you increase the field, you increase the density, and so because it's essentially proportional to B divided by the square root of density, the value is not very different from machine to machine. But what is the point is that in most machines, in all machines that we can think of, the Alfvén speed, which is the phase velocity of this wave, is slightly below the birth speed of the alphas. In other words, the speed corresponding to the 3.5 MeV that the alphas have when they are generated by fusion reactions, which means as the alphas slow down by collisions, they are bound to encounter the resonance with the Alfvén speed. So if you like, they become excellent surfers. In other words, they are perfect in catching the wave of Alfvén. And catching the wave of Alfvén is good for the surface, if you like, but not very good for us, because the alphas are very, very many. If you like having zillions of surface on a wave, which can resonate with the wave. So the alphas can actually drive the wave unstable. But once the wave is unstable, it can grow to large amplitude. And then, like for the surface, the wave can actually push the particles that resonate with it and kick them out. And so this can be a problem, because the particles are kicked out early in their slowing down. They cannot provide the energy back to the plasma fuel. And so we have a very, very big damage in reactivity, even maybe stopping it completely. So slowing down alphas can resonate with Alfvén waves. The Alfvén waves are driven unstable if the pressure gradient of the alpha is strong enough. And of course, if the drive of the wave, if you think in linear terms, is sufficiently large that it will exceed the damping of the wave, there will be, of course, some elements, some mechanism of damping of the wave in the plasma. So this balance between drive and damping is essential. Now, in tokamak, I don't want to go through the complexity of the geometry, but just want to tell you that the Alfvén waves, which in space are like really waves on guitar strings, the tokamak are a little bit more complicated. They have a character of eigenmodes, and they have different kinds of frequencies. Nevertheless, they always have the same phase velocity. And this is a very nice example of a success of MHD theory, because theory has predicted the structure of these modes in a very esoterically looking derivation, but beautiful and clean. And then whenever we measure, we find exact same thing as the theory predicts, at least in the sense of the presence and structure of these waves. So that's perfect. Now, these waves can be what we were fearing will happen, that is a loss mechanism for the alphas during their slowing down. So we have to make sure they don't get unstable, or at least not so strongly that they grow large. So that is why we study the stability of the wave. Are these real? Yes, they are real, they exist, they've been observed, and they are also seen to indeed affect the confinement of the fast ions. And this is an example put together by Rich Horiluk of many cases in which you have a fraction of the alphas of the fast particles, in this case simulating alphas by NVI and SRH, a fraction that is lost as a function of the power, or also in terms of the mode amplitude. So of course, the larger the power, the larger the mode amplitude, and the larger the loss fraction. Now, the trouble is in ITER and demo, you can only withstand very small fraction of loss. Not only because you ruin your reactivity, like as I said before, but even worse, you actually have concentrated losses on specific points on your machine, and you can really make a damage to the machine locally and that's terrible. So the question is, can we make sure they are stable, and can we somehow anticipate the nonlinear evolution in case they're unstable? And just to give you a flavor of what we can do to look at the stability, I give you an example of the study we conduct. So stability is given by balance between drive and damping. The drive, as I said before, is associated with the, if you like, the thermodynamic potential, that is the gradient of the fast particle pressure, and also by a term in the number that describes the drive, which is essentially the growth rate, which measures or quantifies the proximity to resonance. You need to be resonating with the wave, otherwise you don't interact efficiently. On the other hand, there is the background damping, which is by Landau damping, so non-collisional mechanism, other ways, mode conversion to other waves, or other mechanisms. So there is a whole theory of the background damping. I just want to highlight the very nice small, I mean, not small, but simple experiment, how you actually measure the damping, how you can see what damps most effectively the waves. And this is a technique we develop a jet using different kind of coils. So the idea here is to just, in the absence of fast times even, you inject the wave and you see, if you like, in a cavity that the tokamak represents for this wave, the quality factor of the cavity. So you sweep the frequency of your antenna and you see the plasma response to it, and the width of the plasma response, in essence, gives you the damping rate. If you like, is the quality factor of your cavity with respect to this particular wave, of course. So having the damping rate, then you can optimize your shape of the plasma or your conditions, or whatever, to maximize the damping rate, which is good for us because that will prevent the wave from existing or from growing to large amplitudes. And that is to, this plot is to give you an idea of how successful this is. You can even in real time track the mode with very clever algorithms to define the frequency of your sweep. And you can see that as the Alphen frequency varies, because, for example, in this case, the density was varied, I believe, you can actually see your mode existing very beautifully and very cleanly, and you can see the evolution of the damping rate of it in an experiment which is in relevant conditions, but without the need of the presence of fast times, without the need of the presence of alphas, which is, of course, very difficult to have. So this is real-time tracking. And just to give you an idea of the potential implication, you see that the edge shear, so the, if you like, how steep is the Q profile at the edge, how the safety factor profile at the edge, how that influences the value of the damping. And if you are on the left part of this plot, the damping is low, which means, potential problem. The drive can exceed the damping. If you are on the right-hand part of the plot, when you have the damping over the 2%, if you look at all the points, these are recent measurements. And so for the moment is the trend that we look at. 2% is fine, 0.2% is not fine. So that is to say that we can now have an idea of how to optimize that. So I close this part of the presentation. And first of all, let me ask you how much time I have in general, if I...
Like 4 minutes.
4 minutes to conclude?
Yeah.
Okay.
Because we have after like 15 minutes for question, but maybe you could extend a little more.
I would need a bit more if you don't mind.
Yeah, like
so because I wanted
your time. Just I will have 15 minutes more.
Okay, I will then go back to the
yes, Ambrogio, your session goes until 15:30, so that of course includes the Q&A, so you can decide how to manage that.
Okay, I will go quickly through that. I wanted to give you an idea of the objectives we have for Horizon Europe, and this is one key point is to optimize the chance of success. This I said before, then I made my parenthesis on burning plasma physics, but we have to work on the building blocks, final jet campaigns, building blocks on the medium-sized tokamaks. As you know, probably, well, I mentioned that to you, a few of them have now made upgrades to look at the specific issue of the heat exhaust. we will have the first experiments in JT60, so in Japan, on the, let's say, more steady state plasma scenarios. We will have a first operation on the compact subgrade tokamak in the Czech Republic, which will look at the possibility of having liquid metal on the walls, and the first steps to the first DTD plasma. Now, we're also looking a lot at the theory and simulation work. We have set up what we call advanced computing hubs for high performance computing, for code integration, for data management. And okay, I'll just skip this. And we plan on them to be really a backbone of our effort. We look at the stellarator, and the stellarator as an alternative approach to fusion power plant. As you know, the main stellarator that we have in Europe, and I would say in the world, is Venus 7X, which has already exceeded expectations. It has set the record for the fusion performance in stellarator, and now is preparing a crucial campaign, which would be to actually work with actively cooled divertor in the different spots distributed around the structure of the stellarator, as you can see. I wanted to say that we are looking at the materials. I'm sure you have different lectures on materials. So just to remind everybody of how difficult is the question of material for us, because we have also the scales and different disciplines, because we have to cover all the problems that happen to our structural materials at the macroscopic scale as well as the microscopic scales. And one of the things that we are very happy to conduct is the construction of the design of the source that will test materials with the appropriate spectrum of the neutrons that will be provided by this source. Of course, this irradiation volume will be relatively small, and so we need to extract from that small volume what would be the impact on large components such as those that we have for demo. But nevertheless, this will be a game changer in what we know about the materials and about the effect of neutrons on their performance. This is the EPFL donors facility, which has been approved and now is going forward. There's been a ceremony a couple of days ago with the royal family from Spain and the government of Croatia, because it's issued from a collaboration between Spain and Croatia. It's going to be built in Granada, close to Granada in the south of Spain. So the fantastic project for a very crucial development in view of demo. And what is demo? That's our approach to the next step before commercialization. Hundreds of megawatts of electrical power, closed fuel cycle, that is, we produce our own tritium, and a plant that will be available on a level that is compatible with commercial deployment of fusion. I want to say a few words about this because this is crucial. I want to underline that we need to capitalize on the fusion intrinsic safety features, which I already mentioned as one of the missions for our consortium, and bringing the technology to adequate maturity, yet trying to maintain the cost relatively low. Now, we had a review of the program last year or a couple of years ago, and we had a number of recommendations, and these are crucial for us. We want to move from research-oriented to design-driven. This is not that research is not an important element, but it's not the drive. The drive is the design for demo, which means we need to have a core of a team somewhere, and in the moment is in Garching, and the demo central team provides a core for then launching this activity, which has been already being launched. What are the critical problems? Again, plasma scenarios, as I said at the beginning, crucial problem for demo as well. We need to ramp up the discharge, keep it stable, avoid disruption, and ramp it down safely. We want to understand the details of how you breed your own tritium, and of course, this has to be done in a sense that's compatible with remote maintenance. And remote maintenance is actually the main driver for the design. How you extract the parts of the diverter needs to be replaced from time to time, the parts of the blanket, and so on and so forth. So this is a very complex activity that we need to undertake at the European level in order to really be credible in our design. The layout of the building is something that, we start from the physics of plasma. Typically, I'm a plasma physicist, it's not a criticism, but now we have to start actually even from the layout of the building, because at the end of the day, this has to be an industrial facility that produces energy in a reliable way. As I said, we need to train the next generation of fusion sciences engineer. I don't need to convince you about that, but I want to convince you about that. Is that we want to promote innovation and European industry competitiveness in fusion. So we have to open the door to innovation, strengthening technology transfer and spin-offs. All the initiatives in that respect have to be helped. And don't think that they're not present yet, because there are quite a few, and I want to really underline this. Of course, we need to foster them and amplify them and increase the number, but they're already there. I don't know if you know, but I want to tell you that we use superconducting cables and superconducting components and technologies that we develop for fusion for example, MRI, for health. For the point of view of materials, we have developed explosive 3D metal forming techniques for pressing metal sheets that are used for cockpits for civil aeronautics. We have developed membranes of palladium alloy for treating chemicals that are used for automobile industry. And as I said, remote handling is a central element for us. And this was really advanced at JET, and has been applied for high energy physics, space, nuclear, and even surgery. And as I said, important to you to know, we are opening to public-private partnerships to expand and facilitate our program. We need to optimize the mechanisms to do that. So education and training, I don't need to dwell on it. What we will do in this coming year, in fact, next year, sorry, it will be a facilities review. That is, we want to understand which facilities we have that are essential for fusion, which facilities we need to procure that are essential for fusion, because we don't want to have any gaps in our R&D, in our effort towards a reactor. So conclusion is that the key word, and I think I'm more or less on time, plus or minus a few minutes, the key word for us is integration. I want you to go out of this talk also with this in mind. Integration means integration of different fields of science and technology. All of you have different competence, and you'll develop more competence in different fields. All of them are needed together, but we need to put them together, as I said. Integration between reactor-focused R&D and also spin-offs application. Integration between academic and industrial approaches. Both of them are completely relevant. Integration between consolidating what we know already and innovating. Integration between many systems, and that's crucial, that form the power plant, but also integration between different generations. And that is a crucial element in our field, which is a transgenerational effort, of course. An integration of all beneficiaries and associates and partners, of which you are a fantastic examples. And I'd also like to conclude with this figure on fairness, openness, commitment, and diversity that has become our mantra in Eurofusion. Thank you very much for your attention. I look forward to your questions.
Thank you very much, Professor, for the inspiring talk and engaging talk. So I will read some questions that they have wrote on the chat. Usually we struggle with finding ways of reducing microstabilities and turbulence. Are there phenomena in a tokamak plasma where actually the turbulence results being good?
In which turbulence is good, you said?
I will read it again. Usually we struggle with finding ways of reducing micro instabilities and turbulence. Are there phenomena in a tokamak plasma where actually the turbulence results being good?
The last part is not too clear to me, but you're asking where cases in which turbulence is a good thing to have?
Yeah, if there is, exactly. Could be any phenomena where it is actually good to have turbulence?
I mean, turbulence, in a sense, helps transport. Now, in general, we fight the battle to reduce transport. for most of the plasma, but there's parts of the plasma where we don't want to hold the particles in for too long. For example, the so-called helium ashes. So when we have burned our DNT, we produce helium, and the alpha particles have to slow down, as I said. When they are still hot, they are the most precious particles we have in there. We have to keep them there. So we have to avoid all these issues with the macroscopic waves. But once they have slowed down, they are not of use to us. So that would be good if they are kicked out by turbulence. So in that sense, it's good. There are also aspects of turbulence at the very edge where turbulence could help in the diffusing a little bit the heat by diffusing the particles and reducing the concentration of the exhaust power into small areas of the parts that face the plasma. In that respect, if you have turbulence that spreads out a little bit if you like, the channel through which the heat is deposited on material surfaces, that is good. So in that sense, that kind of turbulence we welcome.
Okay, thank you for the answer. And here there is another question. It says, is it possible to see our effect in either higher confinement regimes beyond the each mode?
Okay. Of course, this is possible. As I said, it's a new regime that we didn't know, that we don't know about, the burning plasma regime, that is, which could have another way of self-organizing than the H mode, the L mode, or the conventional regimes that we know today. It could be, for sure. Now, it turns out that, for example, the H mode is very good for confining the core. Now, you know, the H mode has what we call a pedestal. So there's a steep gradient at the edge, which raises the whole plasma up. And then the inside of the plasma, as a consequence, is very high in pressure. So it's high in performance. But it's great for the core, not so good for the edge. Why? Because this very steep gradient at the edge drives very violent instabilities we call edge localized modes, ELM, ELMs. Sometimes you have heard about ELMs. And ELMs are a disaster because they are very, very violent instabilities at the very edge, which sends out, massive amounts of particles and power on specific, parts of the vessel, and we don't want them. So much so that we actually build the coils inside the vessel to try and tame what they do. So perhaps the H mode is not the best thing to have, because despite the good core confinement, it has this very violent instability at the edge. So perhaps we have another mode that may be related to the different aspects of the plasma that would be good confinement in the core, but perhaps less good confinement in the edge. That would be the holy grail. We don't know for ITER if we can have that. We are looking at ways to have that for demo. One of the ways we can think of for having that in demo is to change the shape of the plasma, making an inverted triangle. At the moment, it's a triangle with the long part facing the center. If we have the inverted triangle, which we call negative triangularity, it looks like, from preliminary experiments on our own tokamak in Lausanne and also on the larger tokamak, for example, in California, D3D, it looks like you can have the best of both worlds. In other words, the good confinement of the H mode in the core, but not this steep gradient at the edge, and therefore not the violent instability at the edge. That's one way we could have, good confinement and not violent instability. In other words, something different from H mode.
Thank you very much. So for now, we don't have more questions. I don't know, Dario, if we should move or.
Yeah, I think if again, thank you, Ambrogio, for joining us for this this last session of the event. It's always really good to have your insight and all your explanations on the work being done now. And I know, as you were a long-standing member of the Academic Council of FuseNet, appreciate that you are still
I'm
supporting.
very, very close to FuseNet, and this kind of events in particular, I think, is a fantastic initiative, and so I'm always supporting it. And,
appreciate it very much. We're happy to be able to count on you for this. So I think if there is no more remarks or questions for Ambrogio, I think thank you, Paula, for the moderation of the session as well. You know, Paula is part of the Student Council of FusionNet, and they're also involved in the organization of this event. So, well, I would like to thank all the attendees as well, and the speakers, and also the executive office colleagues here at FusionNet. So thank you, everybody, for being part of the event. I would like to leave with just a few comments on what we hope that this has been a useful event for you, master students, in many different ways. We hope that, of course, from the scientific and technological point of view, you were able to see the different activities and challenges that are currently being undertaken in the fusion field. Some of these challenges we are working, we as the fusion community are working very effectively and strongly on solving them. But of course, there are several challenges left for the upcoming generation of fusion researchers. So we hope that you are eager to to take on these challenges and help the whole community to move forward towards this roadmap that we have up to fusion electricity generation. So from that part, we hope that this has been useful for you in your scientific career, but also we also hope that it has been useful for you to know a little bit more about the FusionNet Association, the activities and initiatives that we have for you, and all the benefits that that you can have by being part of this network, and that you profit from these opportunities as master students, because as I mentioned, it's the right time for you to be able to utilize to the maximum the activities that FusionNet does, and especially the support we have for improving your scientific career. So yeah, we are always available for you, and yeah, let us know. Follow us on our channels for more direct information. Thank you for being here, and we hope that this initiative will continue for the next year. So we want to give you this overview all the time, checking up the new developments in fusion, and also trying to build community within the students, and yeah, strengthening all the fusion network that I think is really good for the future development as well of fusion. So thank you very much to everybody, and yeah, let's stay in touch.